Hey, Mr. Manwaring and...
Dr. McGee, ready here to talk to you a little bit about voltage and resistance.
That's right, Kirkwood School District. Yo!
Here's our goal.
There we want you guys to be able to do is understand the effect of resistance on current being transferred within a circuit.
And we'll talk a little bit about more resistance. We're also going to hit a little bit on voltage, as we said earlier. So potential energy is any energy that an object has as a result of where it is in relationship to where it's going to be, okay? And we'll talk a little bit more about voltage in a circuit.
Right. Basically, batteries and how batteries work and how those sources of energy work is by providing a potential difference, which makes the electricity flow. If you think about one end of the battery is the positive, one end is the negative. Imagine the negative end of the battery needs to give electrons away.
Mm-hmm.
The positive end wants those electrons, so that is the difference between those two ends of the battery.
And that's measured in what's called volts.
Yeah, volts.
Okay? And that's why you can have like a 9 volt
right.
or a 1.5 volt battery. It's a difference in the amount of...
Right, and that's why you have some little adapters that you plug into your different electrical devices that actually take that potential difference and turn it down just a little bit because your device doesn't need that much voltage
That's what
to
Mr.
run.
Manwaring wants to do to me all the time, is just turn me down a little bit. You're too loud, relax.
Okay, moving on.
Voltage causes current in an electrical circuit to flow. Without that difference, electrons would not be able to flow.
Right, remember, they don't want to move. They don't want to do work. They want to stay where they're at, but once they see there's a difference, they actually start to move towards that.
Electrons don't want to move?
Right.
Or don't want to do work?
That's right.
That sounds very familiar. I'm just
we
saying.
would be talking about
Sixth graders!
sometimes.
Oh, I'm just saying, not all sixth. I'm just saying.
So if you think about a roller coaster, right? You're at the top of the hill of the roller coaster, not a lot of energy. Usually it's the anticipation of about to a drop, and then you go down, and that potential difference is basically the difference from the top of the roller coaster to the bottom of the roller coaster. So that's basically, think about it like the positive end of the battery, negative end of the battery.
This, by the way, is a picture. I didn't take this picture, but this is my favorite roller coaster in the world.
Is that snow?
Yeah, it's called Top Thrills Dragster, and it's in Sandusky, Ohio. It goes 120 miles an hour. Amazing. Check it out. It's pretty cool. Okay? All right. So what is resistance? Resistance is a measure of how difficult it is for charges to flow through a material. The greater the resistance, the less current there is for a given amount of voltage. All right. Now, there are basically 4 factors that determine resistance. This is a picture straight out of your textbook. It's pretty awesome. It talks about water flowing through a pipe. So we're going to hit that and talk a little bit more about how that is kind of like a circuit.
Yeah,
okay?
or you think about something that's real simple, like my daughter loves Slurpees. So if you talk about a Slurpee straw versus a regular straw versus one of those little coffee stirring straws, and the amount of energy it takes to draw up the liquid through those different types of straws,
really
you kind of make that connection to electricity.
Okay.
So there's four factors.
Do the first one. Tell them about the first one.
Material. Some materials are conductors, like we talked about before, and some are insulators. Some are good conductors, they allow electricity to flow through them easily. Some are poor conductors. So, for example, gold's a very good conductor, but very expensive, versus copper, which is also a good conductor, but is cheaper to use. So sometimes we have to just use to be, thinking about money and finances, make sure it be something that's affordable.
Now, how long that item affects the amount of resistance. So longer wires have more resistance than shorter wires, okay? Think of water. If it has a longer distance to travel, it will slow down over time, just the way electrons do.
That's right. And then the diameter, again, getting back to the straws, right? Wide straw versus skinny straw. The wider the straw, the thicker it is, it's going to be easier for the electricity to flow through it, or the water. The thinner the straw, it's going to be harder to flow.
Very cool. And last one, temperature. Now, this is fascinating, okay? The resistance increases as the temperature increases. That means a colder temperature, it's actually easier for electricity to flow through. This is the opposite of really what you would expect, but
yeah, you would.
It is true.
It is very true.
All right. Now, we're talking a little bit about the path of least resistance here,
right,
too.
basically, it's like a person doing the easiest thing possible, like the shortcut way to get home, or cutting through someone's yard to get from one place to another. Not a good idea.
Not a good idea, by the way. Yeah. And electricity will do that exact same thing. So if you're looking at a circuit, here's our battery, here's our light bulb. Now you see the electricity can flow from the negative end of the battery out, up, around to the light bulb, and then back. Or it could say, I reach this spot right here and go, let's see, I'd like to light up a light bulb or do nothing.
I think it's going to do nothing.
Right. And we get a situation where we have what's called a short circuit.
That's right.
Like a circuit that I would make.
Moving on.
Okay. So another example of that, I want to take you to a little diagram. It's pretty sweet. Check this out. All right, we got a little circuit here, and we've got two of them. Let's focus on this top one right
Short
here.
it out. Short it out.
Short it out. Short it out. Okay, so you see it's working right here. We've got a battery. We've got the electrons flowing right up here.
Notice on the top branch, it's not moving at all.
Not moving at all because it's not connected. Now, when I connect that, this branch will have less resistance than that lower branch. Are you ready to do it?
Let's do it. God.
You ready? Ready to do it?
Actually,
Wait, you want me to do it? I'm doing it. Oh, fire! Yes, fire!
see the fall of flame at the bottom? Basically, this is what causes a lot of fires in homes when you have a short circuit. So a lot of times around the holiday times when you have Christmas tree lights and whatnot, basically if you plug too many things in there and there's a short somewhere, you're going to cause a fire.
Right. Now notice what happens to the pacing here of those electrons as they flow around this new path.
I'm just mesmerized by how
Yeah.
fast they're moving.
They're moving very fast because there's no resistance to slow them down, okay? Now, let's go back down here to the bottom one. Now, let's say, and this is a typical situation that I get with my students, is that they will hook a switch up to their circuit, and they'll be like, oh my gosh, Mr. McGee, look! This switch is open and the light bulb is on.
Your students really sound like that?
No, I just made that up. All right. So you can see the switch is open, but yet the light bulb is on. So you would think right now, if the switch is open, the light bulb should be off. Well, what they did is they created a branch here that has no resistance. Any predictions about what's going to happen if I close that switch?
I don't know.
Let's do it. Boom! Now take a look. The light bulb went off. The light bulb's not working because this branch has more resistance than this branch, okay? With a parallel circuit, you got to be careful and watch out for that path of least resistance.
A lot of times you'll find that the battery will get warm
Very hot.
or the wires will become warm.
Yes.
It's usually an indication you have a short circuit.
Yeah, so you want to make sure that you pay very close attention to that because it could be a very dangerous situation.
Yes, it can.
Very dangerous. All right? Okay. So if you have that backward switch, you know that you have created a short circuit, and you got to watch out for that. You got to be careful of those situations.
Absolutely.
All right. Now, the way that kind of innovation has came along and improved a lot of these switches is now we have dimmer switches. Tell us a little about dimmer switches.
Well, dimmer switches basically control the amount of resistance in the circuit. So basically, you can increase the resistance or decrease the resistance, and as a result, the bulb or light that you're controlling
Or fan,
will get,
or
fan,
motor,
right,
yeah,
or
yeah.
we'll get what brighter or dimmer, and we
Right.
use these all the time. Restaurants use them.
Mhm.
You might have been in a restaurant and sitting there eating, and all of a sudden the lights get dimmer around dinner time because it's getting perhaps
Later? Yeah.
later, darker
Sure.
outside.
So you can see you might have sort of the dial one in your kitchen or living room or house. You might have one of these slider ones, okay? But basically they do the same thing. They control the amount of resistance. Now here's the tough part. As you increase the resistance, your light bulb is going to get dimmer, okay? So that dimmer switch actually, once again, that inverse relationship where one thing goes up, the other one goes down.
So you're decreasing the energy in the circuit?
Well, you're decreasing the flow of
Oh,
electricity.
the
flow of
flow.
electrons.
Okay, gotcha.
All right. So our goal was
Basically, for you guys to understand the effect of resistance on current being transferred within a circuit.
and there are 4 things that I hope you wrote down that you paid attention to in regards to how we can control resistance, how a dimmer switch works, and then what happens if you have that really bad scenario of a short
And then
circuit.
please don't talk like Mr. McGee was talking.
No,
I hope you don't
do
sound
that.
like that at all.
Don't do that. Peace.